Hello, everyone. This work by all these fine people is on the definition of RDMA, remote direct memory access. And it has not much to do with memory management, but don't worry, it's not very technical. It's just a few examples to learn what RDMA is about. So we are focused on networks of computers. So a lot of different computers plugged in together and exchanging data. And the problem is that the traditional way of transferring data from one computer to another is rather slow, in the sense that you have your CPU that needs to pack your data through applications, library, operating systems, drivers, etc., transmit it through TCP, IP, and connections. And then on the other side, on the remote computer, you need to unpack the data similarly. And this is very slow, by which I mean about 1 millisecond. So in most cases, we don't care at all. But if you want to push computation to its limit, we can do a bit better. And the way we do a bit better is with RDMA. So this is your computer. You have a CPU, and you have a memory. And that's basically all you need for a computer. Nowadays, we still have a few more stuff plugged into your computers, like input-output, sound card, graphic card, network card. NIC is for network interface card. And in the 80s, 90s, there was a design choice that everything else should be plugged to the memory and not to the CPU. It kind of makes sense because otherwise your CPU will spend a lot of time transferring and moving data around. And so this architecture was called direct memory access. At least it's explicit. And so engineers got interested in this network card because it has, well, direct memory access, and it is also connected to the rest of the world. And so they came up with RDMA, remote direct memory access, where remote computers can ask your network card to directly modify your memory. And the important part is that your CPU is completely unaware that anything is happening. And that's how we get to lower latencies. And so it was mostly developed for high-performance computing, because that's where you care about having very low latency. But nowadays, it's getting more widespread, so there's more usage in, let's say, data centers if you want to back up data of a database. And if you have a proper setup, you can get down to about a microsecond of latency. So that's very performant. So that sounds good, but the issue is that RDMA was developed by engineers, and so it was created not to make sense, but to go fast. And so our job was to make sense of it. And even if it's like 20 years old, basically we have the first formal mathematical definition of the semantics, of what is supposed to happen. And so we developed an operational semantics, also a declarative semantics, proved equivalent, and we did a bit of testing. Before I can get to a few examples, I still need to say what a program is. And so we have, as I said, a network of nodes, nodes being computers. Each computer can have several threads, and each thread can communicate with other computers. And so a program looks like this. You have usual x86 operations, so read, write, so about everything you want. And it follows TSO because TSO is a memory model for x86. And with RDMA, we bring two new operations, remote write and remote read. And when you see this little n as superscript, it means that it is on another computer. So x to the n assign y means you read your local copy of y on your computer, you send it over the network, and you ask the remote computer n to modify its value of x. And this one is similarly in the other direction. You ask the remote computer to read the value of y and to send it back, and you modify your value of x. And poll is used to wait for an operation to finish, because at some point you need to make sure that it's finished. So one example that basically tells you everything you need to know about RDMA. We have two computers. The left computer has a variable x, the right computer has a variable z, and the second computer does nothing. There's 0 threads, nothing. And on the first computer, you have one thread with two operations. So z and to assign x means you read your local copy of x, you send it over the network, and you modify z. And then you can change the value of x, which is a normal x86 operation. Of course, if you do it in order, well, you still have z equals 0 at the end because you send the whole value of x. And where RDMA is interesting is that z equals 1 is also allowed. And if you're used to weak memory models, it makes no sense at all because usually you try to make sense. Well, threads try to at least pretend that everything stays in order. And in RDMA, they don't even bother. The way it works, sorry. Here's basically your setup. You have your left computer with thread 1, memory, network card, connected to network card and the second computer. And since the first thread needs to communicate with the other computer for this operation, we need a connection. And so this connection is represented by a communication between the two network cards, but also the thread needs to communicate with the network card on each side. And so there's two memory locations that are reserved for communication between the thread and the network card. So when thread reads z assign x, he sees that it is an RDMA operation and just sends it to the to-do list of the network card. That's not his job. It's not the CPU's job. And so the network card, whenever it feels like it, can just pick up the job from the to-do list. And so what makes this weird reordering behavior possible is twofold. First, the value of x is not read by the CPU. It is going to be read by the network card. And the second is that the CPU is not blocked. The whole point of RDMA is that you have your CPU doing computation on one side and the network card doing data transfers in parallel. And so the CPU can go ahead and modify the value of x in memory. And then what happens is about what you would expect. The network card can pick up the value 1, send it over the network to the second computer, and the second computer is going to send it to the remote memory. Also, the second network card is going to send back an acknowledgement that's going to find its way to the memory of the first computer so that the CPU can know it's finished. And so the way you prevent this reordering, if you really want things to happen line by line, is that you need the CPU to wait for the operation to finish. And the way to do this is to add this poll operation. And the poll operation will consume this acknowledgement and block the CPU until it does. So if you do the same thing, you send it to the to-do list of the network card, it's picked up, but now the CPU is blocked. And so now the network card has to read 0, send it over, modify it does nothing, gets back the acknowledgement, and the acknowledgement is going to be consumed by this poll operation. And now the CPU is unlocked and can modify the value of x. Of course, that's just with one thread, and so RDMA starts being more complex, let's say, when there's multiple computers, multiple threads, and stuff like that. As a quick example, if you have two remote computers and you send messages to two remote computers, everything is completely independent. So if you send a message to computer 3 and then to computer 2, your network card might decide to send the second message first. And of course, if you have multiple threads, you have complicated interactions. For instance, if you do a read on Z and a read on X, and the other computer is modify X and then modify Z, you are able to have it out of order and read the value of X first. And so having B equals 0. The reason is pretty similar. The first thread sends everything to the network card because it's not his job. The network card transmits operations one by one. And what happens is that the remote network card is completely allowed to read the second first. As I said, it was not created to make sense. It was created to go fast. And turns out it's faster, somehow. And so then the second CPU can modify the values. And then the first value is read. And everything is sent back to the first computer. And the value of A is modified with 1. And the value of B is modified with 0. And so you get this weird behavior. There's a lot more weak behaviors we can get into, but I probably don't have the time, so maybe later. And so most of our job was formalizing these semantics, and so we have an operational semantics for it. Actually, we have two. One concrete, which is very close to hardware, but it's a bit more intuitive, but bigger, very larger. And we have a simplified one that is equivalent, but that does not really correspond to actual buffer in hardware, so it might be a bit difficult to follow. So we have two of them. And it is, as I said, an extension of TSO, as in we assume the CPU follows x86 memory model. So there's still store buffers that I didn't show previously. And also, we defined declarative semantics for RDMA. So if you don't know what declarative semantics means, it's not very important. But the gist of it is that an operational semantics is very detailed. And it can be a bit problematic sometimes. For instance, on the left, that's the example from 2 minutes ago. And so if you want to prove that this behavior is possible in operational semantics, you need maybe a dozen pages of inference trees and a lot of rules. And if you want to prove that this is allowed in declarative semantics, well, you have your proof on the right. That's it. That's all you need. And the way it works is that everything that happens in this example corresponds to a graph, to a node in a graph. So on the first thread, you read Z, you modify A, you read X, you modify B. Well, you read Z, you write A, you read X, and you write B. Same on the other side, you modify X and Z, while you have two events modifying X and Z. And the way declarative semantics works is that then you had dependencies, so relations between events. And there's a lot of hand waving here, but basically you had a relation from A to B if you have a legitimate good reason to believe that A happens before B. For instance, here you said that you see that Z modifies is modified to 1, and later you will read Z as value to 1. Oh, yeah. And so it makes sense that if you read Z to 1, it's probably happened after the value was modified. So you have a legitimate reason, and you add an edge, a reads from edge. Same for the other one. You read the value of X to 0, and you know that there's some event that's going to modify into 1. So once again, you have a legitimate reason to believe that this read to 0 was happened before the write to 1. And so the hard part of declarative semantics is deciding what behaviors are allowed and what behaviors are not allowed. Intuitively, if there's no cycles, everything is fine. And intuitively, if there are cycles, it's fishy. And the point of weak memory models is that sometimes cycles are allowed. And the art of creating declarative semantics is to explicitly tell which cycles are allowed and which cycles are not allowed. So that's what we did for RDMA semantics. As I said, it's still an extension of TSO, so we can have write-read reordering for CPU operations. And you have usual TSO declarative semantics relations, such as read from, reads before, the two I have shown you. Modification order, if you modify a variable twice, the second happens after the first. And we had to add a couple new relations, notably polls from. As I said, polls wait for an operation to finish. And so in the category of legitimate reasons, if you have a remote operation and you wait for it, you have a dependency from the remote operation to the poll that waits from it. And there's another one, but it's for PCIe guarantees. It's a bit complicated. I don't want to get into it. And basically, we have a definition of a program is allowed if and only if some specific calls are not allowed. And the important part is that both semantics are equivalent. So a behavior is allowed with inference trees if and only if the corresponding graph does not have forbidden cycles. Beyond this, we also did a bit of testing in practice to check that our definition actually makes sense on actual hardware. And so we tested basic litmus tests on two setups with InfiniBand and RDMA over converged Ethernet, okay, which are the two main technologies for RDMA nowadays. And the most important point is that we never observed anything that was forbidden. So we did not observe hardware doing stuff that they were not meant to do. So at least that's nice. And another important point is that most of the behavior that are allowed by the specification can actually happen. So we really need to take these semantics into account. You can't just write an RDMA program thinking that everything is going to be fine, because sometimes you have weird stuff happening. Interestingly, most weak behaviors are pretty rare. You need to stress the system and overload the CPUs and the communications to make these reorderings happen. But they are still possible, most of them at least. And that's a summary of what we made. So we have the first formal semantics for RDMA, which is long overdue because RDMA is from the 2000-something, so yeah, 20 years old, basically. We have an operation semantics, declarative semantics, both equivalent. We did a bit of testing to show that these semantics actually make sense. And what we are left to do now is to make use of these semantics to build on top of it. So maybe RDMA libraries, data structures, try to make sense of how do we write RDMA programs to make use of it. So there's still a bit of work in progress. Thank you.
Questions?
So there's a bunch of research in data center systems where people are using RDMA for like disaggregated memory and storage and things like that. So I'm just wondering about future applications of your semantics. Would it be for something like model checking or doing static analysis over those code bases, essentially?
Sorry. Oh. And so in data centers, if you want to replicate, copy data, you want to make sure to not lose data and not to overwrite stuff. So it will mostly be used, I believe, by data center companies that want to make sure that their algorithms actually make sense. And I don't think you need RDMA for daily computations on a personal computer, so probably not on this part.
Hi, cool work. Just a bit of background on RDMA.
Do you have a guarantee of timing? So like if the other node fails, do you know immediately? Do you have like a maximum bound on the amount of time that the write might take or read? Because on the internet you don't, and that complicates things.
Basically, there's a timeout mechanism included in the network layer of RDMA. And so if you don't have a response, you can resubmit the request. And by default, if you do it 10 times, 15 times, and you don't have a response, you consider that the remote node has died or something happened, and you don't know. And the main issue with RDMA is that the semantics, when everything is fine, is relatively well defined. The semantics of error is a mess, basically, and no one knows what is supposed to happen when there's a crash. So hope everything is fine. And if there's a crash, assume that everything is to be thrown to the garbage bin.
Thank you.
So I'm not as, admittedly, I'm not as comfortable with TSO semantics to know if this is applicable, but somewhat in line with the last question, one of the things that sometimes comes up and always makes everyone groan if it does, is the circumstances when sometimes with an RDMA application, you may be potentially adding or removing some of the nodes during execution of the application. Is that something that can be modeled with this?
Not with this work, because we assume a fixed number of nodes, but technically that should be doable. It's just that setting up nodes and removing nodes takes a long time compared to how fast RDMA operations are. So usually if you need to add or remove them, you need to take some time off computation anyway. You don't want to add new nodes while computation is happening, usually.
Other questions?
Thanks for the talk. Great stuff. Did you prove your operational semantic and your declarative semantic equivalent?
Yes. By hand, it's a paper proof. So there's 25 pages of proof if you want to go through them. But yes.
Thanks.
Time for one last question if anyone has one. Otherwise, we can get back on time. All right, thank you.